Here are the solutions for question number 3 from the 2014 examination paper. So you have to plot phase portraits for this planar system and plot bifurcation diagrams for both of these systems. So for 3 part A, here is our Cartesian system. To find the critical points, we solve x dot is 0, y dot is 0, x dot is 0 when x is 0, and y dot is 0 when y is 0, or when y is mu squared. So we have 2 possible critical points. Notice though that when mu is 0, we only have 1 critical point at the origin. So to determine the stability of critical points, we use the Jacobian, dp dx, dp dy, dq dx, dq dy, which you can easily compute to be this. At the origin, j at 0, 0 is minus 1, 0, 0 mu squared, and if mu is non-zero, this is the saddle point. When for the critical point at 0 mu squared, then here is our Jacobian, and because both eigenvalues are negative, this is a stable node. Now it's easier in this case to plot the phase portrait when mu is non-zero, and you can see you have a stable node at 0 mu squared, and we have a saddle point at 0, 0. Now imagine if both of these critical points move closer and closer together as mu goes to 0, then eventually when mu is 0, we get this phase portrait up here. So for y positive, you can see the trajectories just come into the origin, as in here, trajectories come into the origin, but when y is negative, they move away. And remember, this is a non-hyperbolic system, which we looked at systems like this in the first year. And remember, these trajectories look like this for this non-hyperbolic system. The bifurcation diagram, you'll notice that there are 2 critical points. The origin is always unstable, so that's the dashed line. And this critical point here, you can see, is always stable when mu is non-zero. And this curve here is given by y equals mu squared. So y dot is 0 when y equals mu squared. So this represents the second critical point, which you can see is always stable. So this is the bifurcation diagram. For the polar system, we have r dot is r times r minus mu squared, and theta dot is minus 1. You'll see that r dot is 0 when r is 0, so that's the critical point of the origin. Or we also have a limit cycle when r is mu squared. So this represents a limit cycle. Okay, it may help you here to plot little phase portraits down below. So you'll notice that when mu is positive, we have a critical point at the origin and 1 limit cycle of radius mu squared. Now if you look at the phase portrait, if r is less than mu squared, so if we're inside the limit cycle, r is less than mu squared, then r dot is going to be negative because r is less than mu squared. So r dot is negative, so your arrows point in. Outside the limit cycle, so if r is bigger than mu squared, then r dot will be positive. So here you'll notice that we have an unstable limit cycle and the critical point of the origin is stable. So that's why we have this dashed curve here. This represents the unstable limit cycle. And when mu is negative, we get exactly the same picture. So that again, we have an unstable limit cycle and the critical point of the origin is stable. And that concludes the solutions to question number 3.